So this time we want to know, or we want to find, minima and maxima algebraically. If you remember, we have seen it graphically, right? And it's easy to eyeball it graphically. It's probably one of the easiest job to uh, eyeball and find the minima and maxima, right? But what happens if we want to find it algebraically? Then we have a problem. Okay. So before we want to find it, before we go for the algebraic approach, we want to see some uh, required theorems for it. The first one is the extreme value theorem. What does it say? It says if a function is continuous on a closed interval. Now, the first question would be, what is a closed interval? Anyone? Just don't eyeball the slides. Just try to use your intuition. What do you think a closed interval would look like, or a closed interval would mean?
Would it be you have a hard right and left limit on your function?
Would you please elaborate it, maybe?
So say like your left limit is something like -3, -3, and then you have your right limit, which is 3, 3. If it's continuous in that, but that's a closed interval, it has a minimum and a maximum and a minimum value, right?
Ah, I didn't get that, to be honest. No worries. Anyone else? Let me see if we can find anything else.
It's continuous at all points on the interval.
No, I'm talking about a closed interval. Don't worry about the continuity or anything else.
Like it includes both ends of the interval.
Exactly, that's it. It includes both endpoints. That's what a closed interval would mean. That means if you pick a certain uh, boundary, you'll definitely have two endpoints, right? And if the boundary, I mean the entire uh, space, whatever it is, generally it's the real number line in our class. So if that includes the two endpoints as well, it may or may not. It doesn't necessarily mean that it has to include the endpoints all the time. It could include either of the endpoints. It could even include neither. So if it includes both the endpoints, then we call it a closed interval. And that's the naive definition, though. We have a more sophisticated definition um, using analysis. I'm not going to go to that direction anyway. But yeah, that's the most uh, naive definition you can remember. And the algebraic expression looks like this, right? You need to add brackets, right? Instead of parentheses. Parenthesis is for the open intervals. So if you use brackets on both sides, then it's a closed interval. That means whenever you'll see a question. Um, maybe I'll give you a question. I set up a question with brackets on both sides. I may not write that it's a closed interval. You can actually eyeball it and see that it's definitely closed. Okay, the next thing it says, um, if a function with this type of interval, that means with a closed interval, if it's continuous on that interval, then the extreme value theorem says it definitely has an absolute maximum and an absolute minimum value on that interval. Okay, so if you know one certain interval where you can eyeball the graph, that the the graph looks like continuous, that means it doesn't have any break or any hole, that means it keeps going on in that interval. What happens after or before that interval, I don't care. Only on that interval I can see that it's continuous. Then on that interval, definitely I can say that it has an absolute maximum and it has an absolute minimum. Again, I'm repeating, on that particular interval. It could be different for that same function in another interval, but on that particular interval, we can conclude using this theorem. Now let's see how. Let's say we have this graph on our left. So from A to B, if I say that this function is continuous on this interval from A to B, the closed interval A to B, because I can say it's a closed interval because you can see the endpoints are included, right? You can see that. So if I say that this function is continuous on this closed interval AB, do you agree? That's the first thing. Do you agree that, yeah, it looks like the function looks like continuous here? Do you agree with that? Just try to eyeball it.
Yeah, there's no breaks in that function.
Right. No breaks, no hole. At every point on this interval, you have a defined value. So if I say that it's continuous, I guess most of you will agree, probably all of you. Now, forget about the extreme value theorem. Let's just eyeball it. Let's just try to see if we can actually generate the same result. So if I eyeball it, I can see we can pick a point which is larger in terms of value, of course, which is larger than the others. That means I can say that there is a value which is maximum. And we can eyeball it, right? If you eyeball this graph, this point on our left looks like, in terms of the value, looks like bigger than the others, right? It looks like it's on this graph, it's actually on a higher position than the other points. So I can say on this interval, this is my maximum value. Do you agree? Same goes for this point. This point, I can see the graph has reached its lowest point. This graph on this interval doesn't have any value lower than this. So we can say we have a minimum value for this particular interval. This is our minimum value, right? Excuse me. And now quickly, let's see what happens if it's not continuous. Let's try to eyeball this interval from A to C for this function g of x. So first of all, does this interval AC look closed or open?
Open.
You can see it's open, right? Because there is no defined value at A, neither at C. I mean, for this interval. We do have a defined value though, but that's for C to B anyway. But from A to C, we don't have a defined value. So definitely, either way, since this is open, this interval can't be closed, because for an interval to be closed, both endpoints have to be included, and that's not the case. So if we consider this part of this graph of this function, you can see that we can't really decide, using the concept from the previous discussion. If you remember, we did discuss this part. Using this concept, we could say that there is no maximum or minimum for this function, for this part of this interval. Do you agree? And same goes for this one as well. For this part, from C to B, we do have a maximum value though, but we don't have a minimum, since it's not closed, because for B, we don't have a defined value. If one side is closed, doesn't matter. Both the endpoints have to be included for this interval to be closed. And that's not the case. And you can see we don't have the minimum value here. So that's what the extreme value theorem says. Okay. Okay, we'll come back to this graph, but before that, any question? Any questions so far? No question at all? Okay. If you don't have any question, then you can move to the next one, this graph. And this is quite interesting. And you will soon see why. Okay, so when I'm saying that absolute maximum, then that actually means there could be some other types of maximum value, right? Because this absolute maximum means that there is no value, bigger than that on that graph or for that function. So what could be another type of maximum? So we could say a local maximum. We could try to define a local maximum. Now you might be wondering, what is that? What is a local maximum? So if you eyeball a graph, let's say a graph like this, you will see several ups and downs. You'll see several change of direction. It's going up, 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 and after a certain interval, it again starts going down, and it keeps doing like this. So if you pick up a certain interval, you could find a maximum or a minimum value on that. But if you consider the entire graph, that may not be the maximum value for the entire function. If you, for example, if you just pick up this particular, let's say Q, okay? If you just pick up this point, Q, and if you look at the nearby points, you'll see this is the maximum value you have, in your neighborhood. And this looks like, at P, this looks like the local minimum for that. Okay, or if you consider even smaller interval, let's say pretty close to Q, then even this point at R could be a minimum value for this function, for a really small interval, right? But if you consider the entire function, you could see this is not really the uh, the most minimum point. That means there is a point, at least there is one point which is actually lower than this in terms of value. And there is this one. This value is actually below these 2 points. So you could see for the entire function, the lowest possible value is defined as the absolute minimum, and the highest possible value is defined as the absolute maximum. But if you consider a small neighborhood, you could see some other minimum or maximum value for that smallish neighborhood you pick up. But that's only local maximum or local minimum. So fortunately, algebraically, you will be asked to calculate the absolute maximum and absolute minimum. You will not be asked to find the local maximum or local minimum, but from the graphical approach, you might be asked to find the local minimum. And it will be mentioned for which part I want you to find the local maximum, or vice versa. That means the local minimum. Okay, so this part is again pretty easy. We're just trying to define it differently so that whenever you pick a small neighborhood, you could, you might be wondering, hey, this looks like a maximum, then how do I define it? That's how you define it. You call it local maximum. And whenever you see the bigger picture, you take the entire graph, then whichever looks like the highest point, you call it the absolute maximum. Okay. Okay, let's look at the definition. So just pick up one interval, let's say I, and if C is within that interval, this interior point means C is actually in that interval, C lies in that interval I, and if the functional value of C is greater than the other functional value on that particular interval, then it's the local maximum. Like this one, as I said, this Q is in this interval PR. Let's take this interval PR. Okay, so this Q lies in that, and if you take the functional value at Q, which is this, it's actually greater than the other functional values in this interval. Do you agree? And you can eyeball it, right? If you go both sides, you could see this is the highest functional value on that interval I. Okay, then we say it's the local maximum, and it's local minimum for the other direction. That means if it's the lowest possible point on that interval, then it's the local minimum. Okay. Now, if I give you a graph like this, and if I say, can you find the absolute maximum and absolute minimum from it? And the answer should be yes, you actually can, right? You can find the local minimum and local maximum, or the absolute minimum or the absolute minimum from it. For example, if I say, okay, let's pick up this one, from A to Q, from A to Q, or no, let's pick up this one. Let's pick up R to B, okay, for this interval R to B. So can you locate the local maximum and local minimum? Anyone? from this interval R to B, by the way? Can you locate the local maximum or local minimum?
The local maximum would be S, and then the local minimum would be at point B.
Very good. You can see at S, the functional value for this interval, at S, the functional value looks like it has reached its peak. It has reached the highest point for this interval, right? And again, at B, you could see it's the lowest possible value on that interval you could see. So this is the local minimum. This is the local maximum. Is this the absolute minimum? If no, then where can you see the absolute minimum?
No, the absolute minimum is located at point P.
Very good.
Point P.
Right. And what about the absolute maximum?
Looks like
Point Q.
Sorry?
So it looks like S and Q are equal, like in terms of how their maximums are. So it could be either S or Q.
To me, it looks like, yeah, equal as well. Yeah, then we have actually two peak points. And this is not an exceptional case. You know, when we'll be finding the absolute maximum value, we might encounter a problem like this where we'll get two absolute maximum points. I mean, there could, for a particular function, there could be two peak points. No worries with that. Okay. All right. Okay. Now, a very good graphical representation of what happens before and after the maximum point. So if you remember the sign of the slope, right? We do know the sign of the slope. How does it behave on a particular point? So if you remember, if the slope creates an angle greater than 90 degrees, we say that the slope will be negative. I mean, the sign will be negative. It will be a negative slope. And if it creates an angle from 0 to 90, then we say that the sign would be positive. And I actually said what's the reason behind it. If you just take the tangent of it, tangent of uh, uh, any angle in between 0 to 90, it will be positive. And if you go beyond 90 up to 180, you'll see it's negative. Same goes for secant as well. The slope of secant actually has the same reason behind it. If you just pick up the angle and find the secant value of it, you'll see from 0 to 90, it will be positive. From 90 to 180, you'll see it's negative. And why do you think it happens? So if you look at the graph, let's go back to the previous graph. Yeah, this one. Let's take this maximum point. Now, if you pick up any point from this part, you know, after the peak point, you know, when it starts going down, and if you pick any point from it, if you try to draw a slope, if you try to find the slope, you will see that these graphs will go like this. Do you agree? These graphs, if you, let's say we are picking up this point, and if you try to draw a line, you'll see the graph will look like this, which will create an angle more than 90 degrees. Do you agree? Just try and draw a line on any of these points, or even pick 2 points for the secant line. It will still be the same. So if you draw a line, you'll see this will go like this. As you can see the direction I'm going, and it will definitely create an angle more than 90 degrees with the x-axis, right? So that's why it will be negative after the maximum point. Okay, and if you go from to your left from the maximum point, and again if you follow the same procedure, you will see if you pick up any point from this part of the graph, it will definitely go like this. Just try and draw a line like this. Don't trust me, okay? If you go like this, it will definitely create an angle less than 90 degrees. So that's what it says. Before the maximum point, your slope will be positive. Do you agree? Do you agree with this? Okay. Now let's move on and see. Okay, yeah, we are very close to the concept of finding the local minimum and maximum algebraically. We're slowly moving there, slowly and really slowly going to that. Before that, we have one more theorem, which is local extreme value theorem. And what does it say? It says if a function has a local maximum or a local minimum at C, and if the derivative exists, that means if it's differentiable at that point, then the functional value at that point, the first derivative at that point will be 0. Okay, that's pretty interesting. You might be struggling to understand the uh, you know algebraic statement of this theorem, but it's really intuitive to understand it from the graph. Let's see it. Let's see it from this graph. Yeah. So the statement says if you have a local minimum or a local maximum at a point, let's say we have, although it has written C, it should be A, as you can see, right? That's a typo. It's not really C. Either you need to rewrite it as C or you need to rewrite it as A. It can't be A here and C here. Anyway, I think that's a mistake. That happens, no worries, as long as you understand it. So let's say that's C, okay? This is not A. So at C, we have a local maximum. We can see that, right? We don't have the other parts. Let's just consider for it now. We have a maximum point here, right? And it's continuous. There is no break. There is no corner point here, right? There is no hole here. So using all the required conditions, I could say at this point C, this function looks like differentiable, right? If you don't remember the conditions for being differentiable at a point, you can go back to the slides where it's written, but not now. Just for now, trust me when I'm saying that it's differentiable at this point. But when you're done, you can always go back to the drawing board and check your concept again, okay? So it looks like this function, this graph is differentiable at this point C. Okay, and now the statement says the first derivative at this point will be 0. Now what does that mean? So if you remember, the first derivative is actually really related to the tangent, right? If we can draw a tangent at that point, this is the peak point, right? The red dot. if we can draw a tangent at that point, you could see it will go like this. Whenever it's a maximum point or a minimum point like this, when you can see a change of direction before and after the point, if you draw a tangent line, it will always go parallel to the x-axis. Not always though, as I said, if you see a change of direction like this, upside down mug or which will look like a bowl or something like that. I mean, change of direction before and after the peak point or the lowest point. If you draw a tangent line on those type of points, it will see you will see that it goes like this. It goes parallel to the x-axis. Now the question could be, what's the slope? What's the instantaneous rate of change at that point? Can you see that? Forget about the algebraic notations and all that.
Is it 0?
And why?
Because if you're at the very top of your graph, well, you're just gonna have a straight line across, shouldn't you? Because at least in this point, you have a bell curve. So if you want to just touch your line, you have to be just touching the tip or the top of it.
Right. And if you see the other side of it, it's creating either a 0 degree or a 180 degree angle with the x-axis, right? Do you agree? This line, well, it's creating, it's parallel, and a parallel line, we don't need to go any further. We just know that a parallel line creates either a 0 degree or a 180 degree with the axis. Excuse me. And we know that the value of tangent of 0 or tangent of 180 is 0. You could see the other side of it, right? Obviously, at the peak point, we know that the instantaneous rate of change is 0. And even if we calculate it using the tangent, still you could see the tangent of 0 or the tangent of 180 is 0. And that's what it's actually trying to say. This is the first derivative. That means it's the instantaneous rate of change at this point. We know that, right? And it is 0. Definitely it is 0. And you can see it from the graph. Now, this is what we need to find the maximum and minimum values algebraically. This is the first thing we need. We will actually we will need some more calculations, some more definitions, but this is the first thing we need to calculate it algebraically. Okay, so the critical point, what's that? So a critical point is if you pick up a point where you could see the first derivative is 0, or at that point the derivative does not exist. That means that on that point the function is not differentiated. We say that it's the critical point of our function. That means whenever I give you a function, if I say find the critical point for me, you just need to find the first derivative of that function, then set that to 0 and solve it. We'll see examples of it, okay? I'll show some worked out problems, but that's the definition, okay? All right, now let's see what did I mean when I said the derivative does not exist, okay? All right, So if you look at this graph on our left, you could see at C, the derivative does not exist, right? Because if you come from the left, it takes you to this point. I mean, when you approach C, if you come from the right, it still takes you at this point, but at that point, the functional value is not the same. There is a hole here, right? So we say that the first derivative or does not exist, or in other words, the function is not differentiable at this point, right? But you can still see there is a local minimum at C, right? If you pick up a certain interval, you'll see this defined value. Can you see that? This defined value, this black dot, signifies that it's a local minimum. So that could be one of the uh, uh, ways we could say that it's that at C we have a critical point, and still the function is not differentiable at that point. This is a critical point, okay? Because there exists a local minimum at that point. Same goes for this one. We have a maximum because it looks like a peak, right? It looks like a highest point for this graph, but it's not really differentiable. Can anyone tell me why, real quick? If you remember the criteria of being differentiable, of course. Anyone?
Because it's a corner.
Exactly, it's a corner point, right? It is a corner point. So it definitely is not differentiable at this point, or rather on this point. But still, we'd see that at C, we have a critical point. If we solve it, I'll show examples of it. You'll get critical points here, okay? Okay, what could be another exceptional case? So if you see a graph like this, I guess this looks like the graph of x cubed, although it's not the graph of x cubed, because it would have been going through the origin if it was the graph of x cubed, but it's quite similar to the graph of x cubed anyway. So let's say you have a graph like this, okay? And at C, you could see the first derivative is 0, right? The first derivative is 0, but there is no local minimum or maximum here. Do you agree? Because if you consider this point, you could see there is a lower value here and a higher value here. And if you even if you pick a smaller interval, you could see there will be points lower than this, or rather I would say smaller than this and higher than this, right? So there is no local min or local max at this point C, right? So all of this, again, we haven't really seen the algebraic approach as yet. Bear with me for that. But for the graphical approach, you could see these things could happen. That means even though even though there is a local minimum, the function could have a hole. That means it may not be differentiable at that point. Same goes for the corner points. I mean, there could be a highest point or a lowest point at some point, but it may not be differentiable at that point. And a function could have no local mean or local max at a point, but it still could have zero first derivative at that point. Okay, so I might give you graphs like this and then tell you, describe which situation it is. There will be options and you need to pick the right option from the given 4 or 3, how many are on offer. You just need to see which situation fits the graph best, and then you just need to pick up that option from the multiple choice question, of course. Okay, so if I give you a graph like this, you'll be given several options, and obviously one of the option will say that on this point the first derivative is 0, but you don't have any minimum or maximum value. You just need to pick that option. Okay, any question from this? No question at all? Okay. Okay, yeah, one more scenario before we take a break. So if you have a graph like this is even more interesting. Obviously, there is no local min or local max at this point, right? Because it looks like the maximum value is here and the minimum value is here. So at C, looks like there is no min or max value, right? And even more interesting part of it is it's not even differentiable at this point. Can you see that? Because it's creating a vertical line. It's creating a 90-degree angle with the x-axis. It's absolutely parallel to the y-axis, right? So if that's the case, we know the tangent of 90 degree is undetermined. We can't really determine the value. So that's what we get from this, right? It's vertical, or it's parallel to the y-axis. That means it's creating a 90-degree angle with the x-axis. So it's not really differentiable at this point, and neither it has a local mean or local max. That could be another scenario. And you might see questions like this. You'll be given a graph and your 4 options could be this one, 2, 3, 4. And you need to pick the right option. Okay, just eyeball the graph and see what's happening there. All right. Okay, now we'll take a 5 minutes break, and finally we'll be calculating the local mean, or rather the absolute maximum and absolute minimum using the algebraic approach. Okay, all right, so let's meet at 10:07, and hopefully we can solve some problems when we return. Okay, I'll see you in 5 minutes. And what should you do? So the first thing is we need to find the critical points. That's the first thing. That means we need to set, we first need to find the first derivative. We need to set that to 0 and solve it. Or we might want to see for which value our first derivative does not exist. Okay, whatever it is, we want to find it, and I'll show examples of both. And then we just try to see or evaluate the function at those points. That means the critical points and the endpoints. We'll evaluate the function at the critical points and at the endpoints. And definitely we'll see, we'll be able to find or locate the largest and the smallest value, and this will give us our required absolute max and absolute minimum. So let's see one example, and then we can reiterate this probably, hopefully, and it will be more convincing by then. So let's say we have a function. Let's start with the easier one. And this function is, let's say, x to the 4 minus 2x cubed. Okay, let's try to find the local min and local max from it. Okay, so what's the first thing we need to do? Again, we just need to find the first derivative. That means we need to differentiate this. So what's the derivative of x to the 4? Anyone?
Four x to the third minus 6x to the second.
Just do it. Let's do it one by one. So yeah, the first one is 4x to the third using the power rule, right? We know the derivative of x to the n is nx to the n minus 1. On this occasion, for this particular part, I mean the first term, x to the 4, the n is 4, right? So it's 4x to the 4 minus 1. That's how we get 4x cubed. And for the second part, again, we'll be using the power rule, but we can also use the constant function rule to keep the constant 2 outside. We don't need to do anything for that. For x cubed, using the power rule, it will be 3x squared, right? Because n is 3 on this occasion, so 3x to the 3 minus 1, which is 3x squared. Do you agree? This is for the second term, by the way. So that means it's 4x cubed minus 6x squared. Any question from this derivative part before? Because if you can't find the first derivative properly, then you might be reaching a different and perhaps wrong result. So you need to find the first derivative properly. You need to do it. Need to do it in the right way. That's the first thing you want to do. Any question from this? No question at all? Okay, what's the second thing? What's the next thing I would say we want to do? Anyone? We want to set this to 0, right? So just do this, set this to 0, and solve it for x. So 4x cubed, oops, minus 6x squared equals to 0. Now, how do I solve it for x? How do I find the values of x? Anyone? It's pure algebra though. There is no calculus here. What should we do? You need to go back to the algebra class for this. if you have the notes, if you have the PDF files or anything related to the algebra class, you might review this before you start finding the local the absolute max or min, because you will be doing this so many times. You will be solving this for x so many times. So if you somehow don't remember, you can always go back to those resources you have from the algebra class and review those, because you'll need this. So what should you do? Anything out of your head? Even you're trying to say anything? Because I can't hear anything. Now looks like no one is trying to say anything, but at least give it a try. It's from the algebra class again. So you can at least give it a try, even though it's wrong.
You're going to want to find the common factor so that you can simplify it.
So what's the common factor here?
For this one, it would be 2. Or, 2x squared, sorry.
2x squared, very good. Yeah, we can factor out 2x squared, and then we can simplify our life. So if I factor out 2x squared, we have 2x in the first term, and in the second term it will be 3. Do you agree? I've just factored out the common thing from both the terms. It could be more than 2 terms, doesn't matter. Whatever you have, you just need to factorize it in this way. The best way to solve is to factorize it this way. If you can factorize, then definitely your life will become easier. So now, if we solve it, that means x squared is 0, or 2x minus 3 is 0, right? Because if you have 0 as the product of more than one expression, then either of these has to be 0. Otherwise, the product can't be 0, right? So if we set this to 0, we get x equals 0, and we get 2x equals to 3, and if we solve it, x equals to 3/2. Do you agree? Right?
So there's 2 zeros.
Yeah, it doesn't really matter, to be honest,
Okay.
because if you plug in 0, I mean, let's say you have 2 zeros. So if you plug in the first 0, whatever you will get for the second 0, you'll get the same value. So yeah, you're right. Definitely, there is 2 0 for it. Yeah. All right. So now our next job is to evaluate the function at the 2 endpoints and on these critical points, or rather at these critical points. And then we will be able to eyeball our local max and the local min. So let's say I'm giving you the interval from -2 to +2 for this particular function. Okay. So now we want to evaluate the function at -2, at +2, and at these critical points. Let's do that. So let's start with the leftmost point, which is -2. So at -2, it will be, the function is x to the 4 minus 2x cubed. Okay, minus 2x cubed. Can anyone do it for me? Then at the critical point 0, It's 0 to the power 4th minus 2 to the 0 cubed. This is definitely 0. Then at 3 halves. Can anyone calculate the first one for me? Just use your calculator. 3 halves to the power 4, 2 times 3 halves cubed. And please do the third one for me as well. And at the rightmost point, it will be 2 to the power 4 minus 2 cubed. And it will be 0 as well, because this is 2 to the power 4th as well. 2 to the power 4th minus 2 to the power 4th will be 0. Okay, what's the first value? Anyone?
32.
32. Is there anyone who has got a different result or can verify it for me? Someone else? And what about the third one? Anyone? Come on, you can do it for me.
For for -2, I got 0. I don't know if that's right.
For -2, you got 0.
Yeah, for like the very first one you have.
No, it shouldn't be 0 for -2, that's for sure. Because it's positive 2 to the 4th and it's positive 2 to the 4th. So 2 to the 4th is 16. Yeah, it should be 32. Yep. And okay, let me do the third one. So 3 halves to the 4th minus 2 times 3 halves cubed. So it looks like it's 27 over 16. Can anyone verify it for me?
That's what I got.
Okay, cool. All right. Now, the easiest job is to see and locate the absolute max and absolute min. What do you think should be the maximum value? Or rather, where, I would say.
-2.
-2. It is the max. And what is the minimum? Here, right? So we can say that at -2, sorry, okay, I think that should be fine. At -2, we have got the maximum value, and at 3 halves, we have got the minimum value for this particular function on this interval. Okay. So you can see for finding maximum or minimum value algebraically, it's not that straightforward as the graphical representation, is it? So the first thing you need to do is to find the first derivative. Then set that to 0 and solve it. Or in some cases, which I'll show in the next example, in some cases you will see the derivative does not exist for some points. Find those. Okay, then evaluate the function at the endpoints and at the critical points. And then you can just eyeball it, eyeball the maximum and the minimum, right? Any question from this? If you have any question, I'm more than happy to rediscuss. Okay, although it's a straightforward problem, it's quite an easy one. The homework problems will be much more sophisticated, much more complicated than this. Okay, it may not be this easy, but the idea will remain the same. The calculus part will remain the same. You will have harder algebra to encounter, nothing else. solving this first derivative would be difficult. That's it. Nothing else. Okay. Okay, let's see what did I mean when I said the derivative will not exist for some points. Let's see. And one very good example, let me generate one, would be this one. Yeah, let's start with an easier one. Let's say 1 over, not 1 over, shouldn't say 1 over. We have to have an expression here. Let's say 3x plus 2 over x squared. Okay, let's say we have a function like this. Okay, and we want to find the critical points from this. Again, the first job in our hands is to find the first derivative. Okay, now a quick question: what should we do to find the derivative of this fraction? What should we do? Anyone?
The quotient rule.
The quotient rule. Very good, because it's a fraction. So let's do that. So the first derivative, again, we'll be doing the same thing as I promised. The procedure will be same. The calculation might be complicated. So we know it's the denominator squared, right? And if you keep the denominator, find the derivative of the numerator, minus keep the numerator and find the derivative of the denominator, right? I'm just writing the formula for it. And if I simplify it, it will be x to the 4th. And the derivative of 3x plus 2, anyone? What's the derivative of 3x plus 2?
3.
3, very good. Because you can use the constant function rule for this 3x. So it will be 3 times 1, and 2 is a constant. So the derivative of that would be 0. Okay. And for the next part, 3x plus 2, and the derivative of x squared, I think we have already solved it about 100 times. It's 2x using the power, right? Okay, let's see if we can simplify it just a little bit more. Let's just see. Let's just try and do some algebra. So it's 3x squared. This will give us a negative 6x squared. And this will be a negative 4x over x to the 4th. So it will be a negative 3x squared from this 2 minus 4x over x to the 4th. And I think we can simplify it just a little bit more. If I can factor out 1x, I have negative 3x minus 4 over x to the 4th, and I'll have negative 3x minus 4 over x cubed. So this is my first derivative for this function, 3x plus 2 over x squared. Okay, this is the derivative. Okay, so the first job is done. Next, we want to see what happens if we try to solve it. Okay. So if we set this to 0, negative 3x minus negative 4 over x cubed will be 0. Now this is the place where we will see the derivative will not exist for some points. And those points will also be a part of the critical points. If you remember, we did see some cases in the graphical representation where the derivative did not exist. We'll see it now in the algebraic approach as well. So using the idea of domain, can you remember for what type of values or for which values this might get an undefined value? Can you remember? Could you remember anything out of your head that could lead us? Since it's a fraction, we should have it. It's not the obvious case, of course. Often we see some cases that it's not the case, but at least in most cases, for a fraction, we do get some values for which the fraction does get undefined. Can you eyeball, or do you remember how to find that, how to locate that? No one? So for a fraction, your denominator can't be 0. Now do you remember? If your denominator is 0, then your fraction gets undefined. So in other words, if I try to reiterate it, if your denominator is 0, then for this fraction, it gets undefined. Or in other words, if your denominator is 0, then your first derivative does not exist. Do you agree? For those values which makes this fraction undefined, or which makes the denominator 0 for this fraction, for those values, our first derivative will not exist. Can you look at those values now? Can you see some at least, maybe one value that could make this first derivative undefined? For which the derivative will not exist? Just give it a try. I've given you all the hints. No one? For that, you just need to see for which values your denominator gets 0. So your denominator will be 0 for x equals 0. So this will be a critical point. And if this fraction is 0, that means the numerator is 0. We just need to solve it for x. So negative 3x is 4. That means x is negative 4/3. This is another critical point. So this is the example of the derivative does not exist. And obviously this is for setting the first derivative to 0 and solve it for x. Okay, that means whenever you have a fraction, just set the denominator to 0 separately, and for those values of x, your derivative will not exist, but those values will still be a part of the critical point, like this one. Any question from this before we move any further? Take your time, okay? If you want me to rediscuss any of the things, just let me know, okay? Looks like no question, so we can actually move to the next problem. And obviously, I'll give you a problem, and I'll want you to work in pairs or work in groups for that. Okay, so let me give you a problem and then create a group. So let's do it this way. Let's say your function is fourth over 5 plus. No, let's skip it. Let's do it this way. Okay, let's skip it. Yeah. Try to find the maximum and minimum values for this function in between -1 and 1. Okay.
Just to clarify, that's x to the 4th divided by 5e plus 3.
5x plus 3.
Okay.
Okay, and let me create the group for you. There you go. So either x cubed is 0 or 5x plus 4 is 0, right? If we solve it, we get x equals 0. And from this one, we get 5x equals to -4. That means x is -4/5. Okay. And if we solve this one, we get 5x plus 3 is 0. So 5x equals to -3 and x equals to -3/5. So these are your critical points. 1, 2, 3. These 3 points are your critical points. Okay. And now to find the maximum and minimum value, you just need to take this, or rather, where's this? Yeah, pick up this interval and find the values there. So find f of -1, f of -4/5, excuse me, f of -3/5, f of 0, and f of 1. Remember, you need to evaluate the function at both the endpoints and at the critical points. Now, where did you get the max and where did you get the min? First of all, is there any group which got different critical points than this? Is this the same for all of you? From the first group, did you Did you get the same critical points, same 3 critical points?
Yes, sir.
Okay, perfect. And where did you get the maximum point from group 2? Where did you get the maximum point? Brooke, James, or Matthew? Brooke, can you hear me? So where did you get the maximum point?
I haven't got that far. I didn't really do it because I didn't know how to do it.
I got it at F of 1, but I feel like maybe I didn't do it right.
At F of 1?
Yeah.
Okay. Anyone else got at F of 1? From any other groups? From group 3? Where did you get the maximum point? Group 3? Kimberly, can you hear me?
I can hear you, but we didn't have the right equation to kind of go off with. I think our maximum point was 1, or no. I don't think we even had
Did
one.
you get the same 3 critical points?
We had 0 and -3/5.
We had, yeah.
Okay, so you didn't get -4/5?
No.
Why?
Just because we got the bottom part of the quotient rule, but when we did it, we hadn't done the top part correctly, so we weren't able to get x to the 3rd equals 0,
okay,
or
okay.
Yeah.
Got it. Okay. All right, so let me quickly verify, because I don't think I have enough time for the second one. So let me verify what happens for all of this. And the second one is actually easier than that, right? Did you find second one easier at least than the fraction or the first one? I hope so. Okay, what is the function again? I guess it was x to the 4th over 5x plus 3, right? So let's see. If I plug in -1, it will be negative. It will be -5 plus 3, so -2. So it will be +½ If I plug in 0, it becomes 0. If I plug in 1, it becomes 1/8. If I plug in 4/5, it will be a huge number. 4 to the power 5th, and it will have 5 times 4/5 plus 3. It will be 7 in the denominator, that's for sure. And 4/5 to the power 4th. Can anyone use the calculator for me? And for -3/5, obviously the function becomes, I guess it becomes undetermined, right? Yeah, so 4 times 4, 4 times 4. 16 times 16 is 256, and over 625. So it's 7 times 625, and it's 256. Whatever it is, you need to use the calculator. Okay. Yeah, looks like the highest value is at -1. Do you agree?
Shouldn't that be -1/2?
That's what I go to.
This one?
-1.
Yeah, because
Uh,
it,
Oh, yeah, of course. Yeah, you're right. It should be negative. So then looks like it's at +1. I'm not sure because I don't have the calculator. If you simplify, whether it's actually less than 1/8, I don't know, but looks like, yeah, looks like it's at +1. Is there anyone who has got it at +1? And if you simplify it, what do you get? Just cross check your work, okay? It's 256 over 7 times 625. Just simplify it and check whether it's actually bigger than this 1/8 or not, okay? All right, any question from this before we wrap it up? Any question?